Okay, so we're gonna do the thing where you have a image classifier neural network, and you start with a random image, random pixels, and then you use gradient descent on the pixels to try to find an image that maximizes the output of the image classifier for a particular class. So yeah, we're first going to implement that, which I think will take like 2 minutes, and then that might be cocky, I don't know, but and then we're gonna play around with I guess I think like particularly like frequency components. Okay, so yeah, we basically just need to adapt this code. This is texture generation using a mobile net, and I have a video on that somewhere, and on the channel, but we're not let's see, we're not generating textures. We need to, okay, so let's see here. Load a pre-trained neural net. That's what we're doing. Trained on ImageNet. Okay, so it's 1,000 classes. I don't know what alpha means. So it's 1,000 classes. So I need to get what the classes are, I guess. Which are somewhere, like they're over here. It's in the, decode predictions. Okay. So, I guess we'll just use like a random, okay, so let's see what the output is. Like if I just, so this is a random image, and do we need to pre-process? Because I don't know if this is supposed to be between -1 and 1 or 0 and 1. So I'm just going to run this, and I'm going to not run this. And actually, I should probably just delete that. I don't think I need any of this. I may or may not need to run pre-process. That's the only thing I don't know. So I'm just going to delete that. We don't need a gram matrix. And this will be the training stuff, which we'll get to in a minute. But okay, so right now I just need to see what the shape of the output is if I run a random image through. Wow, that took 5 seconds. That's amazing. That was pretty amazing, actually. Okay, so the output is a 1 by 1,000 tensor. So what we are going to do is say we want an arbitrary class. We want our pixel image to activate a class. So we'll say target class is going to be, and this can be a constant or something. I don't know if that matters. So it needs to be zeros, and it needs to be, I think, 1,000 by 1 by 1,000. Is that like the batch size, the first dimension? I don't know. Oh yeah, but I need to assign, I need to make one of them a 1. Although I guess you could also do a weird thing where you try to like maximize 2 classes simultaneously. What would that do? That would break neural net. No, you never maximize 2 classes simultaneously, son. Okay, so... Okay, I need to assign like an index here. I don't know how to do that. Target class assign. Does this take an index? That would be amazing if that takes an index. Joke, it doesn't take anything. Okay, I need like a random 1 hot. Well, let's just Google that. Okay, TensorFlow random 1 hot vector. Oh. So indices. How do you specify the shape? Depth. Indices. TF fill. Yeah, I need TF fill probably. Dims value. TF fill 2-3 with 9s. Yeah, but how do you specify the shape? Depth. On value, off value, axis, depth of 3. I definitely don't understand that. Let's see if I can experiment to figure it out. Otherwise, I mean, we're just gonna be defeated by a 1 hot vector because we don't know how to make it. So, indices, like 4, 2, 5 needs to be a 1. Depth. What does depth mean? Like, it just needs to be a vector. Like, I don't... Depth. On value. 1. Off value. 0. Axis. Don't know what that means. Okay, that's exactly what I need. Okay, so I don't understand how that works, but that's fine. It just doesn't matter. What if axis? Like, what would axis do? Like, holy shit. 100 by 1. Uh-huh. Yeah. Okay. We'll take it. We'll take it. So this needs to be that. And it's 1,000. I mean depth. Like, what is that? What does depth mean? It just doesn't matter. Okay, so we're gonna implement the actual raining. And okay, so I think I have that here. So I'm gonna get rid of that. Our initial image is a variable because it's going to be updating. And okay, so I'm using like a batch, I guess, of like 16 images. We'll tone that down to 9. Run both images through MobileNet. So this is the prior code, so I'm just gonna kill that. The loss is oh yeah, but if this yeah, because this needs to be a batch now. Okay, let's just say one batch, because I don't know how to make a batch of one hot vectors. Returns a one hot. The locations represented by indices take value on value, while all other locations take off value. On and off must have matching data. Yeah. If the input indices is rank in, the output will have rank n plus 1. If indices is a scalar, the output shape could this be any more complicated? Like, holy shit. Whoa. Shouldn't use profanity. Okay, so okay, if I want to batch, does that mean that I have to just say 42 for blank in range? Like if I want a batch of 16? Yeah, but actually show the thing. Oh, okay. Alright, so we have a bunch of one hots. And they're all going to try to maximize the 42 class of ImageNet, which I don't know what that is. Okay, so we can now have a batch here, and then the overall loss is the model on the initial image. I feel like there's a better way to express this loss. Well, yeah, I mean, you kind of want, like, because these are one hot vectors, so usually people use cross entropy. I'm just gonna use the 2 norm because, I mean, I guess I can change that later. Okay, so it's the model, it's the output of the model minus the target class, right? Perfect. Okay, optimizer. I don't know what beta or epsilon are, so I'm just going to pretend they don't exist. And then, okay, and then the actual training is, yeah. How come I don't have a grid? Yeah, I need a grid. Oh, yeah. Okay. Because we're training on a batch of how big? Oh, 16. Let's go back to 9. You don't want to get too crazy in your batch size. Okay, so that's 9. And training steps. Do all the training steps here. Let's say like 10 steps to begin with. And I think again we just repeatedly compute the loss. And update everything. It's just that easy. Okay, so yeah, but and then the other thing though is you want to clip the pixels. So let's try to do that. Clip by value. Although it's like, I don't know how this affects the, like mathematically if you're, I mean, doesn't that like upset the gradient descent or something? I mean, I guess if the dimension, I mean, I think it just saturates. Like if a dimension hits the max or min, I guess it just sits there for the rest of the descent. Don't know. Okay, so these need to be between -1 and 1. Okay, so let's see if that runs. And print loss.numpy. Okay, let's see what that does. 3 point, oh, it's working, kind of. Oh my god, it's working. Although it's very slow. Although I'm not using the GPU right now. Which is fine, I mean, this... Okay, so... Alright, let's look at what happened. Let's look at what happened. Maybe. So we want to visualize, this is 3, and that's 3. And yeah, is that the whole thing? Well, it's already supposed to be clipped. What are you talking about? Oh no, you're supposed to add 1. This needs to be, because they're between -1 and 1. So you need to add 1 and divide by 2. Right? Which is the same as adding half. Oh man. No, I think you add 1 and then divide by 2. Yeah, but that's the same as 1/2. But that doesn't seem right. Just whatever. Okay. So it shouldn't have to clip. Okay. And yeah, so I think I might need to use the cross entropy. The other problem is that we don't know. Well, the other thing we should do is we should run. Yeah, we should run the these inputs through the model to see what it says, because it should be 42. What? Oh. Decode predictions. Decode predictions. So let's... Okay, that learning rate is probably too high. So like 0.5. And we'll do like 100 steps. And we also want to show the images before training and after training. So this will show them before training. Do I have to say plot.show? I don't know, probably. And this will show them after training. And yeah, so let's see what that does. And I should probably implement the cross entropy loss, but also this image is way too large, but that's fine. Is it not printing the error anywhere? Oh, because, yeah. I did that incorrectly. How many steps are we doing? 100? It shouldn't take that long. Yeah, let me look up the cross entropy loss while that's training. Losses overview. Yeah, no, binary true labels, binary cross entropy, the Poisson loss. Huh. Do I want categorical? Oh, I think I want binary because I'm outputting binary. So label smoothing. Binary cross entropy. Why? So you just pass the true and the predicted. Can do. Can do. This was supposed to give me a notification. There it goes. Okay, so So, I mean, it worked. It's like, you can see that these images have more swirliness to them. Let's see if it actually, if I run it through the model and get the actual prediction. Eager tensor object. Do I need to make this like a constant? Or like, okay. Okay, so the number, so like 0.99, you know, well, let's just look at the actual, it's a gamma. Run it on the initial image. So, yeah. Okay, so like dot numpy, and then look at the first one, and then like look at 42. I mean, they're all like -10, except for 42, which is 0.99. So I think that means the implementation works. It's predicting a gamma, which I have no idea what that is. So let's see, we're gonna do a couple things here. We're gonna make these images much smaller. After training, and it doesn't seem like it needs 100 training steps, so we'll just do it for 50. Okay. Oh yeah, I was gonna change the class because I don't know what a gamma is, unfortunately. Yeah, I'm gonna do that because I need a class that, like, I know what it is. Okay, this is our nice uniform. Is it uniform or Gaussian? It's uniform. I wonder if I made it Gaussian. I mean, what would be the difference? Okay, this is our loss. 1.4. Yeah, I should probably run on a GPU. 0.3. Wow. I mean, that's some pretty low loss. .006. Jeez. I didn't know it could get that low. That is pretty low. And right. So this is kind of the okay, and then just to see what the class is supposed to be. A do-witcher. I don't know what a do-witcher is either, unfortunately. Well, I mean, we can see that right. I mean, I don't know if the res is high enough, but like the trained images, I mean, it's almost impossible to describe, but they do look visually different. but I mean, they certainly don't look like natural images. So, let me try to get a category where... Is there any way I can just look at ImageNet categories easily? ImageNet categories. Yeah, just what are they? Goldfish. Oh, let's do hen. I like hens. Yeah, I mean, like, these categories are terrible. Bee eater? What is a bee eater? Jellyfish. Okay, we'll just do hen. Or stingray. No, we'll just do hen. Okay. So I'm going to make this 8. And I'll run it like for 60 steps, I guess. So, yeah, so I mean, what we're getting is, I mean, it seems like there's a bug. It seems like there's a bug, but I think what's happening is working. It's producing these images that, to a human, look a lot like noise, except they have a kind of weird... I mean, they do have some sort of kind of like clustering in them, but they don't look remotely like a natural image. So that's kind of suggesting that, which also kind of makes sense because, like, I mean, like, if you think about the combinatorial space of the inputs, these are apparently like 224 by 224 pixels, and each pixel is 3 integers between... Actually, I think they're floating point. I don't know how that affects anything. Right, I mean, this is really weird, though, like... Oh, yeah. Okay. So this is okay, so hen. 99% probability that it's a hen. And that's true for every input. All 16 inputs, we push them through the neural net, and it says hen with 99% probability. But, like, it's clearly not a hen. Right? And it's like saying this is a hen. Let's just show 2 by 2, I guess. If I can make it bigger. That too, is that gonna work? No. Is there a way to turn off... Yeah, let's just show one image. Yep, 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 yep. Oh, yeah, because it... I don't know why it doesn't. Okay. Right, there you go. So, yeah, like, this is a hen, according to, MobileNet. I was gonna say, I mean, like, so every pixel, there's, combinatorially, there's like 255 cubed possible pixels, which I think is something like 16 million. And then you have 244 times 240, so you have 16. Is that what it is? Yeah, you have like, yeah, you have 16 million power 244 squared. So that's like your combinatorial space of inputs for MobileNet. And, like when they train MobileNet, like they're only passing in like actual natural images. So, like, I mean, it's only being trained on like an exponentially small percentage of like the combinatorial possible space of inputs. And so I guess like it maybe makes sense that there should be huge numbers of images that to a human look random, but are classified as let's look at the like progression maybe. Why not? Why not? Yeah, let's just look at the progression. Yeah, of just say like the first image. Show. I mean, it's like there are. It seems like there are edges that like pop up. Like it seems like this has stronger edges. But yeah, I mean, it's really unclear why it would. I mean, like, is there any special relationship between like these images and like the natural images? Alright, so let's show our progression of. Okay. Of course, like some of the image artifacts I think are due to the compression, like in the plotting. 2.4, 2.9. I think we're getting compression artifacts from the plotting. Oh yeah, what if I plot the the differences. Yeah. That'll be cool. Why is this darker? Oh, oh, yeah, because I didn't do the multiplication thing. Okay, so let me get the initial image as a just call it iteration 0 is the constant of, hopefully this copies it. Does this copy it? Maybe, is there an explicit copy function? Because copy? Oh, there's no copy. We'll just assume that calling a constant, actually, I guess if I, yeah, whatever. Yeah, okay, let's do this again, and then we need to add 1, and then divide by 2. I need to make the, because we're getting compression artifacts. That's fine. I will ignore that. Also, I wonder if you do like a different initialization rather than like a random uniform. Yeah, like what if you did like a constant? What if your initial image was constant? Right? Oh, what was I doing? I already forgot. Oh yeah, I was gonna do the differences. So we're gonna visualize the differences. Yeah. Hin, 99.98% probability. Wow. And okay, let's visualize another hin. Yep. I mean, it seems like it's creating these kind of edges. It seems like it's creating like pseudo edges. Okay, so let's display the difference. I already forgot what I called it. Iteration 0. Iteration 0. Okay. Alright, so let's display iteration 0. Let's just do it in a different thing. Oh, I don't have to modify that again. Okay, so if I just show iteration 0, it should look like random noise, Does that look different from this? Yeah, I guess it does. Okay. I don't know. I mean, it's like, you know, because your brain is like, oh yeah, there's... Yeah, I can't really tell if this looks different or not, because it seems like it... I mean, it seems like this is more coagulated. It seems like this has some coagulation, and this doesn't seem to, although it kind of does. Okay, so I need to display the differences. So we're norming these to be between 0 and 1. Yeah, so that should be fine. I should just be able to directly take the difference. So, and then we'll just say, we'll just pick, you know, 2 and do imshow minus this. Is this, I guess this could be negative, couldn't it? Yeah. Yeah. That's annoying. So, I think, jeez. I think do the norm after you take the difference. I think that makes sense. Right. So 1.0. I don't know. It doesn't like that. See, I wasn't supposed to do clipping, so why did it clip? I guess because maybe this needs to be 2 and 4, because it could be as high as, or it could be, because if you have like -1 minus -1, that would give you -2. This ain't working out. Div. Okay, but also print np max. And of diff and np min of diff. So I mean, yeah, whatever, just fine. Add 1.0 2. Yeah. So this is what gradient descent added. I mean, that's not really interpretable. So, okay, let me do the thing where I start from yeah, let's do like normal. Let's try to do a normal distribution with like a very small variance, so it's like effectively okay, shape, mean, standard deviation. So we want the mean to be 0 and the standard deviation to be very small. It's like 0.1 maybe. And let's see what that does. Yeah, so you can kind of better see what gradient descent is doing. Like, yeah. It's just adding these weird patterns. I guess it's kind of like a deep dream or whatever. But it's kind of like, I mean, like if you wanted to use this technique for generating images, which is kind of what the current, if you use, it's something like you use clip, wait, hold on, 1.7, okay, I think that needs more training, but let's see what we got. Hen or chainmail. So it is pretty confident it's a hen. Probably needs more training, but that kind of looks like an eye. And okay, this was the difference thing. I'm not sure that matters. After training, it needs to be much larger. Okay, I think it needs to train for longer, so I'll do like a few more training steps. And yeah. Oh, also, let me cancel that because I want this to be larger. Like 12, I guess. Okay. Kiss is the initial. Alright, that's 3.16. Yeah, it just creates these like weird swirls. And then it's like, yeah, that's a hen. But like if you, I mean, to be fair, this does kind of look like a bird. That does look like a bird face, but I should be using salience maps. Also, this isn't converging as well. Two point two. Yeah, it doesn't. Well, I don't know. One 1.007. Okay, 0.035. So, like, it's pretty confident this is a hen. So yeah, I mean, like, they're clearly... I mean, yeah, they just have weird swirly edges. And then it's like, yeah, that's a hen. So, yeah, I mean, let's run the predictions. I think we have 9 images. Hen. Like, the top 5s kind of break down. Yeah, I mean, like... I mean, even in, like, the 5 prediction, like, you're still getting, like, birds. Like, chickens. I think that's a bird. A grouse. I guess that's a bird. An umbrella is not a bird. A European gallinule, which may or may not be a bird. It's just like, could you modify this somehow to, like, stay on the natural image? Because it seems like you should be able to... Like, that's the thing. Like, it seems like you could... I don't know, like, train, like, an auxiliary neural net to, like, recognize this as, like, not a natural image. I also wonder what if you did, like, Fourier decomposition of these images. Like, what would that do? Yeah, I think I might do that, like, in the next video. I might do, like, some sort of wavelet or Fourier decomposition of these images. Because it's like, what is going on, you know? This stuff is crazy. Also, it'd probably be easier if, like, we were working with, like, smaller images, but, oh, yeah. What if we did, just as a very quick... Does this work if you say MNIST? This may or may not work. It's 10 classes. No, it doesn't like it. Oh, I see. You only have 2 choices. Okay. Yeah. Okay. So anyway, well, we'll run it well now. All right, so we got it to work. So like we're taking these weird images that do not look like natural images, and then we're getting like 99.9%, prediction for a class, that doesn't look anything like the class to a human. And so yeah, it's kind of like, why? And is there a way to modify this technique where, you could constrain the images being produced to be on like the natural image manifold? Yeah, so maybe we'll look at that later.